Hello and welcome to another lesson for Math 1106, Math for Business Precalculus. My name is John Adamski. This is week 11 where we'll be discussing exponential functions. The purpose of this lesson is simply to expand our vocabulary of functions to include a new category that we call exponential functions. We'll get to know what those functions are and some properties that they have by looking at their graphs first, through plotting points and sketching their graphs. We'll mention the domain and range of these functions in passing while we are looking at them through the graph. I'll give the formal definition of what an exponential function is, and we'll see how it can be used to model some real-world scenarios. Population growth, radioactive decay. In nature, lots of things can be modeled with these types of functions. When you do reach a calculus class, we'll be doing similar problems there with extra layers added to it. So it's a good idea for us to get some experience with those types of problems now. And lastly, we'll end with a discussion of what we call the natural exponential function. It's a very special and particular exponential function, and one that you will spend the majority of your time in calculus studying. At least when it comes to exponential functions, that is the one that you generally use in a calculus course, and we'll see why that might be and just get us comfortable with what that function is. So let's get to it. Okay, so what are exponential functions and what are they all about? Well, here's one. Y equals 2 to the x. That is an exponential function. And I'll define exactly what I mean by that in just a second. But you notice that the variable x is now in the exponent position. We haven't seen that before, actually. We've looked at plenty of functions that look like, x squared or x to the fourth or something like that, where the variable is being raised to a fixed power, 2, 3, 4, whatever. Now, the base is fixed at 2, and the variable is determining what power we're going to raise that to. Okay? Now, to see what this is all about, let's start by filling in a table of values and then sketching the corresponding points that we get, plotting the points that we get. So anyway, let's start here. When x is 1, this is an easy place to start. 2 to the first power, well, that's just 2. When x is 2, we get 2 squared. Well, that's 4, of course. And when x is 3, 2 cubed is 8. And there's a natural pattern that we see. Every time we increase x by 1, we multiply the output by 2 in additional time, right? X is determining how many times we multiply by 2. All right, can we work that backwards? Can we extrapolate this pattern in the reverse direction? Well, sure. I guess you could say that every time x decreases by 1, we multiply by 2 one less time. Or in other words, we cut the output in half. So we go from 8 to 4, from 4 to 2. If we continue that, I should get a 1 here. And let's just confirm, yeah, when x is 0, 2 to the power 0 is 1. And if there was ever any reason, or if you were ever questioning why 2 to the 0th power is 1, this is why, because it extends the pattern in this direction. And it extends beyond that. What's 1 cut in half? Well, 1 cut in half would be 1/2. What this says is that when x is -1, y is going to be 2 to the negative first power. And what does it mean to raise 2 to the power -1? Well, it means to take the reciprocal of 2 to the positive 1. That, of course, is just 1/2. Right? In fact, it's a general rule that maybe I'll just remind us of, that when you raise anything, say x, to a negative number, okay, what that means is to take the reciprocal of x to the positive version of that number. Okay? This is the definition of negative exponents. Let's just get that on the board. Okay? So if you want to know, for example, when x is -2, what is 2 to the -2? Well, 2 to the -2, according to this rule, 2 to the -2 is 1 over 2 to the +2. So it's just the reciprocal of 2 squared, and that's 1/4. Notice that this is continuing the pattern. As we move up and decrease x by 1, the outputs are getting cut in half, from 8 to 4 to 2 to 1, 1/2, 1/4. The next one should be 1/8, and it is. 2 to the -3rd is 1 over 2 to the +3rd, which is 1/8. Okay? Let's plot those points. So let's see, starting where we did, this would be the point 1, 2. I'm saying 1, 2. That's x, y. That's the point 1, 2. The input and the output can be visualized simultaneously with a point in the plane. That would be 1, 2. That would be right here. Okay? And the next one would be 2, 4. So if I go over to x equals 2 and y equals 4, that would be here. That's another point on the graph of the function 2 to the x. And I also have 3, 8. So I would go over to x equals 3, y equals 4, 5, 6, 7, 8. Okay? Notice that, in the table, we said every time you go to the next row down, the y values are being doubled. In the graph, that's saying every time I move one step to the right, the height of the graph is doubling. Okay? And every time I move to the left, the height of the graph is going to be cut in half. That's every previous row, the y value is being cut in half. Every previous row, the y value is 1/2 of what it was. Okay? So 0, 1 is right here. -1, 1/2. -1, 1/2. Again, every time I take a step to the right, the height of the graph is being cut in half. And at this point, the height of the graph is 1/8, and it's very small. And if you were to extend this to the left, which my table stops here, but you know that the height of the graph is going to continue to be cut in half as I move to the left, so 1/16. Now the thickness of my chalk is going to prevent me from really showing you the detail of the graph as I go to the left, but the outputs are always going to be positive numbers. Maybe you can see that. As I move to the left, the height of the graph is going to be cut in half and cut in half again, but it will never reach 0. So if I just connect the dots with a smooth curve, which is what I want to do, to give you the shape of this graph, this is the shape of this exponential, of the graph of this exponential function. Okay? Notice that it goes through the point 0, 1 as its y-intercept. Okay? Let's look at another one. Here we've got y equals 5 to the x. Now we can do this one a little bit quicker because we did this one very carefully. 5 to the first power, that would be 5. 5 squared, that would be 25. And 5 cubed would be 125. Okay, those are pretty simple. 5 to the 0, well, we know that that's 1. Notice that every time you go to the next row down, the y values are being multiplied by 5, right? As you go from this row to this row, we multiply by 5. And as you go from this row to the previous row, we divide by 5, correct? So we can extend this pattern up. We'll get 1/5, 1/25, and 1/125. Notice the nice symmetry. It's caused by this rule, this definition of negative exponents, but 5 to the first and 5 to the negative first are reciprocals of one another. They're related to each other by just flipping the fraction. 25 and 1/25. That would be 5 squared and 5 to the negative 2 are reciprocals of one another. 5 cubed and 5 to the negative third are reciprocals of one another. Right? When you negate the exponent, you flip the fraction. And -0 is the same as +0, so 1 is the reciprocal of itself. Everything is working out very nicely. What does this graph look like? Well, we can plot these points. Let's start with 1, 5. Okay? So 1, 5, that would be 2, 3, 4, 5 would be right here. And this pattern of every time I increase x by 1, y gets multiplied by 5 shows itself in the graph by saying, and every time I increase x by 1, the y-coordinate gets multiplied by 5. So I need to go to 2, 25. It's already off the charts. If I back my way up, I can get 0, 1. I can plot that, 0, 1. That's right here. And as I decrease my values of x, my y-coordinates get divided by 5. That is to say that when I take a step to the left, the height of the graph gets multiplied by 1/5. Okay? So the height of the graph goes from 1 to 1/5, and then it's down to 1/25 and 1/125. Again, the thickness of my chalk is preventing me from really getting across the detail here, but the graph is not touching the x-axis, but getting very, very, very close and closer still as you move to the left. So I will just do my best to show that by drawing what looks like a horizontal line very far to the left, and then it begins to skyrocket, and it continues to go up, 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 up very rapidly. Okay? It should go through the point 2, 25, and then 3, 125. So the graph extends infinitely far to the right, but it gets so high up that it might look like it doesn't. It might look like this graph goes vertical. It doesn't actually go vertical. It just grows very rapidly. Okay? All right, what about these functions over here? Well, let's see. If I want to plot some points here, let's say 1/2 to the first power is 1/2. That's clear. 1/2 squared, we square the top and square the bottom. That would give us 1/4. And when I cube 1/2, I get 1/8. Cool. Anything to the 0th power is 1. And when I raise 1/2 to negative exponents, I get the reciprocal of what I got when I raised them to the positive exponents. So I just have to flip these fractions to get the values of 1/2 raised to these powers. I'm going to get 2, 4, and 8. Okay? You might notice that that's the same outputs as this function over here, but for different positions. Okay? That is to say that this function of 1/2 to the x, let's just make note, that is 2 to the negative 1 to the power x, right? 1/2 is 2 to the negative 1. And the rule for exponents says to multiply these together, so I get 2 to the negative x. So how is the graph of y equals 2 to the x and the graph of y equals 2 to the negative x related? Well, it's okay if you don't know this, but when you replace x with negative x, what that does to the graph is it reflects it across the y-axis. So I actually know that this graph, when I go to plot these points and produce the sketch of this graph, it's going to look a lot like the graph of y equals 2 to the x. Should have labeled this y equals 2 to the x. This was y equals 5 to the x. The graph is going to look a lot like the graph of y equals 2 to the x, but reflected across the y-axis. We don't need to know that. We can just plot the points. We've got 0, 1. That would be this point right here. And as we move to as we increase the values of x, we get 1, 1/2, 2, 1/4. Every time I increase x by 1, the height of the graph, the value of the function, is being cut in half. And every time I take a step to the left and decrease the value of x, the value of y is doubling. Okay, so as I move to the left, I get negative 1, 2, negative 2, 4, negative 3, 8, 5, 6, 7, 8, and then negative 4, 16 is off the charts. So what does this graph look like? Well, it's getting closer and closer to the x-axis as you move to the right. And as you move to the left, its height is doubling every time x increases by 1, giving it this shape. Okay? So that would be y equals 1/2 to the x. And let's do one more. Let's look at this one. This is 1/5 to the x. Should be able to fill this one in pretty quickly right now. To the first power is 1/5, squared is 1/25, cubed is 1/125, to the 0th power is 1, and raised to these negative powers is simply the reciprocal of 1/5 raised to these positive powers. So we're going to flip those fractions and get the whole numbers, actually, of 5, 25, and 125. If I go to plot these points, good old 0, 1 is right there. So it also goes through this point, as all 3 of the previous graphs did. That's because every number raised to the 0th power is 1. And every time I take a step to the right, the height of the graph gets multiplied by 1/5. Okay, so just one step to the right and the height is already at 1/5. 2 steps to the right, the height is 1/25. 3 steps, 1/25. 3 steps, it's 1/125. It's very small. And decreasing the values of x, as x decreases, every time I decrease x by 1, the height of the graph is going to get multiplied by 5. So if we go to negative 1, 5, that'd be 2, 3, 4, 5 would be right here. Negative 1, 5, negative 2, 25, negative 2, 25, well, that's off the charts. So I can show you a little bit what the graph looks like over here. It's very close to the x-axis, but always positive. And moving to the left, every time I take a step to the left, the height of the graph gets multiplied by 5, giving it this shape where it's just taking off like that. This is the graph y equals 1/5 to the x. Okay? Now, when I connected the dots to produce this sketch, I'm filling in some gaps here. Okay? We were able to plug in integer values, whole numbers, into this and make sense about what it means to raise 2 to an integer power. But there are, of course, lots of numbers between the integers. Like, for example, seems to be saying, if I look at this green graph, it's saying there's some point on this graph where the x-coordinate is 1/2. What's the y-coordinate? Well, what does it mean to raise 2 to the 1/2 power? It means to take the square root of 2. So, oh, okay, you can raise 2 to the 1/2 power and get out some number. In this case, you get out the square root of 2. Okay, well, what about other fractions? What does it mean to raise 2 to, say, the 3/7? Well, I can take that to mean 2 to the 1/7. That's the 7th root of 2, the number that when you raise it to the 7th power would give you 2. And then I can raise that to the 3rd power. So in this way, I can make sense of what it means to raise 2, or any number for that matter, to a fractional power. Okay? And the fractions are what we call a dense set. The fractions are everywhere. If you know how to raise these numbers, these bases, to fractional exponents, then that's enough to really show what the graph is looking like. And I'm just going to say you actually can raise 2 to numbers that are not expressible as fractions. For example, you could raise 2 to the power pi, which you might know is not expressible as a fraction. And exactly what that means is a topic for another course. But just know that when I am connecting the dots with a smooth curve like this, I'm implying the values of what it means to raise 2 to all of these numbers. And you could have questions about what it means to raise 2 to some nasty numbers like 3/7 or pi. And those are good questions to keep in mind. But in the end, this is justified. That the graph is smooth like this, and you can produce the graph more or less by just connecting the dots in a smooth fashion like this. And that's what we're going to do. Formally, an exponential function is any function that can be written in this form, where you have a constant c times a base a raised to a variable x. Okay? The constant c can be any number you want except for 0. If c was 0, then this function would output 0 no matter what x was, and it would be funny to call that an exponential function when really it's a constant function, 0. A needs to be a positive number. That's so that I don't get into trouble by trying to raise a negative number to a fractional power. For instance, if you tried to raise -2 to the 1/2 power, you'd be trying to take the square root of -2. And you can't take the square root of negative numbers. So by insisting that the base is positive, we get around that. And I don't want the base to be 1 because I end up with a function that is really not exponential. Since 1 raised to any power is 1, if a were 1, this function would again simply be a constant. It would output the same output no matter what the input is. So these are the constraints that are going to give me a function that really is an exponential function. Okay? Keep this in mind. We're going to need that when we get to the next section on modeling, that's what an exponential function looks like. Okay, I want to sketch one. I want to sketch this exponential function, 3 times 2 to the x, and I want to compare it to the linear function 3 plus 2x. Okay? First, let's start with just filling in some values here. Suppose I want the values of x to go from, say, -3 up to +3. Okay? When it comes to the linear function, 3 plus 2x, a good place to start is when x equals 0. 3 plus 2 times 0 is just 3. So I would get out of 3. And what this plus 2x part is doing is telling me, well, for every every time you increase x by 1, you should increase the output of this function by 2. Okay? Plugging in x equals 1, we get 3 plus 2, that would be 5. Plugging in x equals 2, I would get 3 plus 2 times 2, that would be 3 plus 4 is 7. And you see every time you increase x, the output increases by 2. Every time I increase x, I just add 2. Okay? And 2 is, of course, the slope of this linear function. And this makes sense. Every time you increase x by this amount, you increase y by 2 times that amount. Okay? And backing our way out of this, we can get to 1, -1, -3. Again, every time you go from one line to the next, you're just adding 2. Okay, and that's what multiplication is. 2 times x. How many 2's do you want to add? X 2's. I want to add x 2's. Okay. What about for the exponential function? Okay, I'm trying to use these same numbers of 3 and 2 to show you how it looks in an exponential function. If x is 0, 3 times 2 to the 0 is 3 times 1 is 3. So both of the functions give the same output when x is 0. But since this is an exponential function, I know that increasing x is going to cause me to double the output, right? If x is 1, 3 times 2 to the first is actually 6. We multiplied by 2 to get from 3 to 6. And if you increase x even more, you're just going to be doubling the output again, and again. Okay? And if you start letting x be negative numbers, then you're really multiplying by 1 over 2 to those numbers. So 2 to the -1 is 1/2. 3 times 1/2 is 1.5. I'll use decimals. Half of that is 0.75, and half of that is 0.375. Okay? So this is what the functions do. And if I look at their graphs, we can see the difference there. If I plot these points, 0, 3, that would be right here. And since this function is linear with slope 2, I know how to interpret this. When I increase x by 1, I increase y by 2. Increase x by 1, increase y by 2. And this is producing points that all lie on a straight line, hence the name linear function. Okay, I'll just try and sketch this as best I can. These should all be on a straight line. That's the line y equals f of x. Okay, and what about the exponential function? Well, it also goes through the point 0, 3, so it shares that point in common. But every time I take a step to the right, I'm not adding 2 to the output, I'm doubling the output. So we go from a height of 3 here to a height of 6 next door, and then the height one step over doubles to 12. Taking steps to the left, the height is being cut in half. So the height should be 1.5 over here. The height should be 0.75 over here, 0.375 over here. The height is getting very close to 0, but never equals 0. Okay, and so the graphs are behaving quite differently. All right. The linear function increases at a steady rate. The slope of this graph is constant, whereas the exponential function seems to be growing slowly at first and then starts to just skyrocket. Okay? This is the difference between linear growth and exponential growth. I want to continue the comparison between linear and exponential functions for just a second. When we talk about a linear function, one way to write it is this form, mx plus b. Okay, and every linear function is determined by the values of these two numbers. We know that m is called the slope, and we know that b can be any constant thrown on the end, and what it affects is the y-intercept. It determines the output of this function when the input is 0. When the input is 0, the output is b. That is to say that 0b is on its graph, b is the y-intercept. Exponential functions, we've seen the definition. Exponential functions are also determined by two numbers. We don't call them slope and y-intercept, but actually this constant c could be called, we could call it the intercept. I don't really know that we have a name for it, but if x is 0, a to the 0th power is 1. So when x is 0, the output of this function is c. So the value of this constant term out front is determining the y-intercept. The y-intercept is 0, comma c. So that they have in common. Now a is not the slope. A is called the base of this exponential function, while m is called the slope. But still, it only takes two values to determine an exponential function. You have these 2 degrees of freedom. You can let these numbers be anything you want, as long as c is not 0 and a is a positive number not equal to 1. So here I'm asking a question that needs you to figure out what c and a should be. It says, find the exponential function that fits the given data. And so your job is to figure out what is c and what is a, given this information about the exponential function. And the first step is to just write down, well, what is this really telling me? When you say that f of 0 is 5, knowing that f is an exponential function, it looks like this. And so f of 0 must be c times a to the 0th power. And you're telling me that it's 5. All right, well, a to the 0th power is 1, so you're really telling me that c is 5. OK, so I'm halfway done. I know that c is 5. If I can figure out what a is, I am done. So what does the second equation say? Well, f of 2, according to this definition of an exponential function, f of 2 must be c times a squared. And that's apparently equal to 80. Now, I already know that c is 5, so I can say a little bit more. I can say that 5 times a squared is 80. And if I divide both sides by 5, I can see that a squared is equal to 16. Now, you could say algebraically that a could either be plus or minus 4 by taking the square root of both sides. But in the context of an exponential function, the base a is not allowed to be a negative number. So I actually know that it's positive 4. Knowing that c is 5 and a is 4 allows me to write down this exponential function entirely. It is 5 times 4 to the power x. That's the exponential function. I was able to figure it out through the clues. This one's slightly harder, but not a lot. The idea is the same. This is a new exponential function, so I know that it looks like this, c times a to the x. I have some clues that are supposed to be just enough for me to figure out what c and a are. So, like I did before, let's just write down what this is really telling me about my function. Well, this first line right here, or maybe this second line, I'll start there. F of 4 is 500. That says that c times a to the 4th power is equal to 500. And this top line, f of 2 equals 100, tells me that c times a squared is equal to 100. OK. Well, here's what I want to do. And you may not have seen this before, so I want to take my time here. I know that c times a to the 4th is 500. And I know that c times a squared is equal to 100. And I know that given an equation, I'm allowed to divide both sides by the same thing. So take a look at this. Suppose I take this first equation and I divide the left-hand side by ca squared, and I divide the right-hand side by 100. So now I'm joining these two equations to make one big equation that says that this fraction is equal to that fraction. And this is true and justified by the fact that what I did is I started with equal quantities that I was told were equal. Ca to the 4th equals 500. And I divided the left-hand side by ca squared while dividing the right-hand side by 100. But I was also told that ca squared was equal to 100. So I did divide both sides of that equation by the same thing, by equal quantities. And the result is a new equation that is also true. That is also satisfied by the same values of c and a. But progress has been made because now I can cancel the c's. I can go one step further and apply laws of exponents that says that a to the 4th divided by a squared is actually just a squared. So this tells me that a squared is equal to, well, 500 divided by 100 is 5. That's a big clue. In fact, now I know that a is the square root of 5. It's not the negative square root of 5 because, again, the base a cannot be negative. For what it's worth, you could also write that as 5 to the 1/2 power. Both refer to the square root of 5. And now that I know that a is the square root of 5, why don't I revisit either one of these equations? I'll just choose to visit this one down here that said that c times a squared is equal to 100. Well, now I know that a is the square root of 5. So this says that c times the square root of 5 squared is equal to 100. The square root of 5 squared is, of course, 5. So we have c times 5 equals 100. And if I divide both sides by 5, this says that c is equal to 20. Now I know what a is, I know what c is, so I'm ready to write down the function. The function f of x is equal to c times a, the square root of 5, to the power x. If I had chosen to write it as 5 to the 1/2, you could have written it this way, 20 times 5 to the 1/2 to the power x. But there's a rule for exponents that says to multiply nested exponents. So a more natural way to write this, the way you would normally see this written, would be 20 times 5 to the x divided by 2. Both are the same, it's just two different ways of writing it. So this is a type of question that you'll see sometimes, and this is how you solve it. Now, exponential functions play a very important role in the natural sciences because they do a very good job of modeling the phenomena that we see in nature. When you think of a population, whether it's a population of rabbits, human beings, or bacteria, populations grow in a certain way, assuming that they have enough resources and ignoring the interaction with predators. When a population is small, and I'm just showing a population graph right now. When a population is small, meaning the height of the graph is not very large, the population will grow at a modest rate. Okay? If you have a small population, then there isn't that much breeding going on. The population will grow, but at a modest rate. Okay, fine. But eventually the population will grow to be a little bit bigger. And now the population has more people breeding, and the population will grow at a quicker rate. Okay? So we can kind of see that now the population is growing quicker. And that causes the population to grow at a later time to something even greater, where now you have even more breeders in the population and more new births, causing the population to increase at an even faster rate. And so this is what we observe in nature. It seems very simple to understand that the larger the population is, the faster it's going to grow. And the faster it grows, the bigger it gets. And this creates a kind of feedback loop that we see in its graph. So this is called natural growth. The larger that the population is, the faster it's going to grow. And conversely, the smaller the population, the smaller the growth. And natural growth, you can see from the graph, the right tool to model this, what we're really looking at here is the graph of an exponential function. And so exponential functions are used to model this type of growth in populations. And here's an example that we can tackle at this point. So it says, suppose a population of bacteria grows exponentially. And from that discussion, that's a kind of natural assumption to make. If the population is initially 225 and grows to 315 after 6 hours, okay, find a function that gives the population of bacteria after t hours. So I want to model this observation with an exponential function. And so to do that, I'll put my work over here on the side. The first sentence is actually very important. That allows me to say, all right, well, the function I'm looking for, it's going to represent population. And ultimately, I want it to be a function of t hours after we make this initial observation. So I'll write p of t, but it's going to be an exponential function. So it's going to be c times a to the, and I'm going to say t instead of x. That's my function. And my job is to figure out what is c and what is a. If I can figure those two numbers out, I'm done. And what am I told? Well, the population is initially 225. Okay, by initially, I'm going to say that that's times 0. Okay? So what I was given is that the population at time 0 is 225. And I'm also given, while I'm at it, I'm also told that after 6 hours, so when t is 6, you can see that I'm using the unit of hours now for my variable t. The population after 6 hours is 315. Okay, so I need to use that information to figure out C and A. It's very similar to the last example. Okay, maybe you know automatically that C is going to be 225. That'd be a very good thing to see. If you don't see it immediately, well, what is P of 0? P of 0 would be C times A to the 0, and that's supposed to be 225. All right, but A to the 0 is 1, so this is really just saying that C is 225. I have one of the numbers. To figure out A, I'm going to go to this next clue that says that P of 6 is 315. Okay, so that means that C times A to the 6th power is 315. And I already know that C is 225, so I can say that this says that 225 times A to the 6th power is 315. Dividing both sides by 225, I find out that A to the 6th power is equal to 315 divided by 225. And it might not be obvious, but those are both multiples of 45. So that is 7 over 5, 7/5. So now you've got A to the 6th equals 7 to the 5th. Maybe I'll just come over here and write that. A to the 6th equals 7 to the 5th. Now we have discussed how to solve equations like this, but maybe it's been a little while. To isolate A, to get rid of that exponent of 6, I need to take the 6th root. And that means I need to raise it to the power 1/6. Of course, I multiply these exponents together and get 1. That was my entire motivation there. And I find out that A is equal to the 6th root of 7/5. Okay, now if you prefer, there are other ways to write that. You can write that as the 6th root of 1.4. Both of these are fine. You can use fractions or decimals. You can use fractional exponents, or you can use radical signs, and you can mix and match them however you want. Okay, so the point is that my function, P of t, is equal to C, which I know is 225, times A, let's write it as maybe 1.4 to the power 1/6. That needs to be raised to the power t. So that's the base, and we're raising that to the power t. That's a little unnecessarily complicated. I think I could write that a little bit nicer by just acknowledging that the nested exponents should multiply together. So I get 225 times 1.4 to the power t over 6. Okay? All right, so that answers the first question. That is my model. Okay? And what this model is good for, why a scientist would actually do something like this, is because now it allows me to plug in future values for t and predict what the population is going to be after t hours. Maybe I only observed it for 6 hours, but I want to know what the population will be in 30 hours or something like that, and I could just plug in t equals 30 and get my prediction. Okay? It is just a model. It is not an actual fortune teller. But the real world is a little bit more complicated. After a certain point, the bacteria will have eaten up all of its resources, and its growth rate will start to diminish, and the whole population will die when there are no resources left. So at a certain point, the model will stop working, but it can predict the future over short time periods. And my last question is to just estimate how long it will take the population to double. Next week, we'll see how we can use logarithms to solve an equation to get a precise answer. But for this week, I just want to play around with this a little bit. If I give myself some t values here and some population values, maybe it's not hard to see. Okay, so the population at time t, that's 225 times 7/5 to the power t over 6. Okay? I'm just replacing 1.4 with 7 over 5 to write it as a fraction. So I know that initially the population is 225. Great. And I know that 6 hours later the population is 315, right? And I know that to get that, I was multiplying by 7/5. Okay, well, the idea here is that every time you wait 6 hours, the population gets multiplied by that same amount. If you wait 12 hours, okay, the population is going to get multiplied by 7/5 again. That is to say, if you wait another 6 hours, the population gets multiplied by that same number of 7/5. The equation makes that clear. If I let t equal 12, 12 divided by 6 is 2, and so you should take 225 and multiply it by 7/5 times 7/5. That is to say 7/5 squared. 7/5 times 7/5. That would give you, well, I don't know. I didn't actually figure out what this is, but I know that 7/5 times 7/5 means that I'm taking 225 and multiplying it by 49 over 25. Right? 7 times 7 is 49, 5 times 5 is 25. And I know that 49 divided by 25 is very close to 2. It's not quite 2, but it's very close. And so that means that this population is going to be close to 225 times 2, which would be 450. That would be the population doubling. So I'm going to say that my estimate for how long it takes the population to double is about 12 hours. Okay, after 12 hours, the population has been multiplied by 49 over 25. So not quite doubling, but very close. So that's a good estimate. Now, as we've seen, exponential functions come in two varieties, depending on whether the base, which is always positive, is bigger than 1 or less than 1. When the base is bigger than 1, we get a graph that is moving up and to the right. We call that exponential growth. When the base is a small number, we looked at graphs where the base was 1/2 and 1/5 in particular. We got graphs that had this sort of shape, where as you move to the right, the height of the graph gets lower and lower, smaller and smaller. Now this is called exponential decay, and it pops up in nature all the time, as, just like natural growth. This is called natural decay. An example of where this would pop up would be, there's something called Newton's law of cooling, which says that if you place a warm object into a cold room, the temperature of the object will start to decrease, and it will approach the temperature of the room. When you put a warm drink in the refrigerator, the temperature of the drink cools down to match the temperature of the refrigerator. But the rate at which it does it is sort of like this. The temperature will cool very rapidly when the difference between the temperature of the object and the temperature of the surroundings is big. That difference will shrink dramatically at first, and as the two temperatures get closer and closer together, the rate at which that object is going to cool off will begin to diminish. Okay? And so it will cool very rapidly to begin with, and then it will taper off and approach the temperature of the surroundings in this sort of way. Another place where natural decay or exponential decay occurs is with the mass of radioactive samples. Now, a radioactive sample is constantly emitting radiation, and as a result is losing mass. Hopefully not very rapidly. The more rapid that this radiation is expelled, the more dangerous it is to be around. But over long periods of time, this effect can be quite dramatic. So, for example, suppose you have a radioactive sample and the mass is decaying exponentially. More specifically, suppose the mass of the sample is initially 6.4 grams, and after 5 years, it's decayed to 4.8 grams. So it will seem to have lost mass through the emission of radiation. Find a function that gives the mass of the sample after t years. All right, so this is very similar to the last example, but there will be a difference. The assumption that we're beginning with is exactly the same. We're going to assume that the function that we're looking for is an exponential function. Now this time it's mass, so I'll use m for mass, and the variable is still time. So I'll call this m of t for mass. And it's going to be c times a to the t. It's an exponential function. Our job is to find c and a. What we've been given in this sentence right here, it says that the sample is initially 6.4 grams. So the mass when the clock strikes 0 is 6.4. And also 5 years later, so I'm going to adopt the unit of years for my variable t. The mass after 5 years is 4.8 grams. That's the given information. And now it's very similar to the last question. I need to figure out what c is. Well, this first sentence right here, m of 0 equals 6.4, essentially tells me the value of c. It says that c times a to the 0 is 6.4. And knowing that a to the 0 is 1, I know that c is 6.4. Great, I'm halfway done. To figure out a, I'm going to use this next piece of information, that the mass when t equals 5, let's see, the mass when t equals 5, according to this, that would be c times a to the 5th. And knowing that c is 6.4, I can actually say, all right, well, that's 6.4 a to the 5th is equal to 4.8. Okay? So this becomes the equation that I'm working with. I have to solve that for a, and it shouldn't be too bad. If I divide both sides by 6.4, that's a to the 5th equals 4.8 divided by 6.4. Of course, you can think of that as 48 divided by 64, and that's 3/4. So there we go. There's 3/4. And if I take the 5th root of both sides, that is to say, if I raise both sides to the power 1/5, okay, then I'll get a is equal to the 5th root of 3/4. Okay, now I know what c is and I know what a is, so I'll write it down. I'll say that the mass at time t is 6.4 times 3/4 to the power 1/5 t. That's c times a to the t. And the nested exponents, this should be a familiar move at this point. The nested exponents can be multiplied together to write this maybe a little nicer as just 6.4 times 3/4 to the t divided by 5. All right, that answers the first question. That is my mass function that I was looking for. Again, why might you take the time to do this? Because now you can predict the future. You can predict how much mass will remain after any amount of time. And I'm asking actually a direct follow-up. I'm asking you to estimate how long it will take the sample to lose half of its mass. Eventually, it will decay to, I mean, it's going to keep losing mass forever. Eventually, it will decay to half of its original mass, which was 6.4 grams. So just to sort of wrap our heads around this, I'll make a small table here of t values and mass values. And the first thing I know is that when t is 0, the mass is 6.4. Okay, cool. Now I know that every time you wait 5 years, the mass is multiplied by 3/4. Okay? I hope that that's clear. Every time in other words, we know that after 5 years, there's 4.8 grams of the material remaining. And the way you get from 6.4 to 4.8, I'm not going to say you subtract 1.6. That would be thinking linearly. I'm going to say that you multiply by 3/4. That's thinking exponentially. How do you cause this change through multiplication? By multiplying by 3/4. And the idea behind exponential functions is that every time you wait an equal time period, in this case 5 years, the output gets multiplied by that same number. So if I wait another 5 years, the mass will be multiplied by 3/4 again. Okay, now 3/4 of 4.8, that would be 3.6. And if you wait another 5 years, the mass will get multiplied by 3/4 again. Every 5 years, the mass gets multiplied by 3/4. 3/4 of 3.6 would be 2.7. Okay? Now, hold up. I wanted to know how long it will take to lose half of its mass. Since I started with 6.4 grams, I'm interested in at what point will I be left with only 3.2 grams? That's half of what I started with, okay? Now, after 10 years, you still have 3.6 grams, so too much. And after 15 years, you have 2.7 grams, too little. Somewhere in the middle, so it's somewhere between 10 and 15 years when you'll be left with exactly 3.2. Now, next week, we'll learn about logarithms and how to solve this exactly, find out exactly how long it takes to lose half of its mass. But for certain, it's somewhere between 10 to 15 years. So as a first guess, that's pretty good. That's true. It will be between 10 and 15 years. 10 years is not enough. 15 years is too much. Now you might want to just take a guess. Any number around the middle of that range is fine. I'm going to say about 12 years. Okay, and I say that because 3.2 is a little bit closer to 3.6 than it is to 2.7. You could say 12.5 years, 13 years, anything like that is reasonable. But I'll just say about 12 years and call it a day. Okay. Join me at my computer so we can look at some exact graphs of exponential functions. This is just Desmos, and I'll share a link to this graph in my notes. What you're looking at here is the graph of f of x equals a to the x. So you can see that over here, f of x equals a to the x, and currently a is set to 2. So this is the graph of 2 to the x. Now we graphed this by hand, so this is not surprising. It goes through the point 0, 1. I can look at that, point 0, 1. And as I move to the right, every time you increase x by 1, the height of the graph doubles. And so this has the characteristic shape of exponential growth. The nice thing about having this in Desmos is I can play around with what that base is. Instead of 2 to the x, I could let the base be some other number and see how that affects the graph. And as the base gets bigger, the graph seems to get steeper. As the base gets smaller, the graph gets less steep. As the base passes through the value 1, something weird happens. When we let the base equal 1 exactly, the graph flattens out. Now that's not surprising because 1 raised to any power is just 1. So this is a graph of a constant function 1. And when the base gets less than 1, then we have exponential decay. Okay, again, we graphed this by hand. This is not very surprising. I can let this be animated. I can watch what happens as the base passes through all these values. It's very pretty. Very nice. Okay. Let me pause. Let me set the base back to, let's just say 2. And let me just point out a nice feature that this graph and all exponential graphs have. If I zoom in on this point, okay, 0, 1, I want to bring in a line segment here just to talk about the height of that point. The height of the point is of course 1. I'm talking about the distance between the x-axis and the point. That's 1, and that's the length of this blue line. If I zoom in on that point, the curve begins to flatten out. Again, this is a curve. You can see that the red graph is curved, but if I zoom in on a single point, like this point right here, eventually you stop being able to see the curvature of the graph, and it starts to look very straight, very flat. And I have over here an equation, don't worry about where it's coming from, but an equation of that line that it's looking like. And you can see that a green line just appeared. And you can barely tell that the green line and the red curve are different. But as I zoom out, you will be able to see that the green line is in fact a line, while the red graph is in fact a curve, an exponential curve. Now the difference is clear. Now the point that I want to make is that as I look at different points along the graph, and I can do that by just increasing this value over here, as I move to the right, the height of the point is increasing, of course, and the slope of that green line, which is tangent to the red curve at that point, is also increasing. So they're both increasing. Both the height of the point and the slope of the curve are increasing. And when I move to the left, the height of the point gets smaller, and the slope of the curve, the slope of the tangent line, also gets smaller. So they're growing and shrinking together. They're related. It turns out they're actually multiples of each other. So if you were to double the height of the graph, the slope of the graph would double, and vice versa. A natural question to ask then is, well, is there any exponential function where the height and the slope are exactly the same? Not just multiples of each other, but exactly the same number. And the answer is yes. If I zoom in on this point, I can see, all right, well, the height of this point is 1, but the slope of the graph is not 1. It seems to me that the slope of this graph is a little bit less than 1. Maybe if I change the base, I can change the slope, and that turns out to be the case. If I let the base increase, I can increase the slope of this line. Well, now I've let it get too big. That slope is bigger than 1. Where do you think 1 is? Well, there's a grid here, and just looking at that grid, I think this is pretty close to where the slope is 1. Maybe a little smaller. Right around there, I would say, is about where the slope of the graph is 1. Okay? So at this point, the height of this point is 1, and the slope of the curve there is also 1. The height and the slope are the same. And that's not true for just this one point, but it happens to be true for all points. So if I let t start to vary, you see that as t gets bigger, the height of the curve gets bigger, and the slope of the graph also gets bigger. As t gets smaller, the height of the point gets smaller, the slope of the graph gets smaller. Let's see how long we can follow this for as we move over here. The height of the graph is going to get very small, and the slope of the tangent line gets very small as well. They're actually staying almost exactly the same. To make them exactly the same, I need that base to be a very specific number. And the number that I need it to be is this number that we call e. Here it is. It's 2.718281828. The decimals do go on and on and on forever. They don't follow any sort of pattern, except in the very beginning it does go 18281828. That's a nice little way to remember that. But after that, there is no discernible pattern. Similar to the numbers in pi, the numbers in e do not repeat themselves. And that's we call that number e, and if I look at the exponential function where that is the base, f of x equals e to the x, that's called the natural exponential function. Okay? And it is the only function whose graph has this property that at any point on the graph, the height of the graph is the same as the slope of the graph. Okay, so that's what we were just looking at before. And we don't need to say anything more about that right now, but when you reach a calculus course, you'll see, for reasons that I can't get into now, that the natural exponential function is the best exponential function to work with from a calculus point of view. This idea of its slope equaling its height turns out to be very nice when working with exponential functions in a calculus setting. So now you've seen it. Just know that this is the natural exponential function and that e is approximately this number right here. That's it.